Today we're diving into the world of AI frameworks and agents. If you've ever wondered how modern language model applications are built, orchestrated, and monitored, this video will break down the essentials. We'll explore LangChain LCEL agent design patterns, Microsoft's Semantic kernel, and more. By the end, you'll understand not just the tools, but also the architectural thinking that powers advanced AI solutions. Let's get started on this journey into the core building blocks of intelligent applications. LangChain is an open-source framework designed to simplify the development of applications powered by language models. Instead of building everything from scratch, LangChain provides a set of standardized interfaces and utilities. This means developers can easily swap between different large language models, manage prompts, and connect to external tools or databases. For example, switching from OpenAI to Anthropic or a local Llama model is as simple as changing a single variable without rewriting your application logic. LangChain's architecture is built around several core abstractions. Model I/O provides standardized interfaces for language models, chat models, and embedding providers. Prompts act as template managers, handling serialization and formatting for few-shot examples. Chains in the LangChain Expression Language (LCEL) allow developers to combine components into end-to-end execution paths. Memory utilities help track and persist conversational history, while tools and agents enable interaction with external systems. Together, these abstractions make building complex AI apps much more manageable. Model I/O and LangChain standardizes how your application communicates with different language models and embedding providers. Instead of writing custom code for each provider, you use a common interface. This abstraction means you can switch between providers like OpenAI, Anthropic, or local models with minimal changes. It's a huge time saver and ensures your application remains flexible as new models emerge. Prompts are more than just text templates. In LangChain, prompt managers handle serialization, formatting, and even few-shot example selection. This means you can easily manage different prompt styles, adapt to various model requirements, and ensure your application sends the right context every time. Prompt management is crucial for building robust, adaptable AI applications. Chains in LangChain let you connect multiple components into a single execution path. The LangChain Expression Language, or LCEL, takes this further by providing a declarative syntax to chain components together. Using the Unix pipe operator, you can pass outputs from one component directly into the next. This makes your code cleaner and your pipelines more maintainable, especially as your application grows. LangChain's memory utilities are designed to track and persist conversational history across stateful sessions. This means your AI can remember past interactions, maintain context, and deliver more coherent responses over time. Whether you're building a chatbot or a complex multi-step assistant, memory management is key to a seamless user experience. Tools and agents in LangChain act as bridges between your language model and the outside world. Tools allow the model to interact with external systems, databases, or APIs. Agents use these tools autonomously, making decisions and executing actions based on the task at hand. This architecture enables truly dynamic and interactive AI applications. LangChain Expression Language, or LCEL, is a declarative language that makes it easy to chain LangChain components together. By using the familiar Unix pipe operator, you can seamlessly pass outputs from one component as inputs to the next. LCEL supports streaming, asynchronous operations, parallel execution, and automated fallback configurations, making it production-ready for complex workflows. Imagine you want to build a pipeline that takes a prompt, sends it to a model, and parses the output. With LCEL, you can write this as prompt model str output parser. When you call chain invoke, the entire pipeline runs asynchronously, optimizing hardware use and handling heavy user traffic efficiently. This approach streamlines development and boosts performance. AI agent is more than just a sequence of steps. Unlike a standard retrieval augmented generation, RAG chain, which follows a fixed path, an AI agent is autonomous. It treats the language model as a decision-making engine, evaluates inputs, chooses tools, executes actions, and dynamically determines the next steps until the goal is achieved. This flexibility allows agents to solve complex, multi-step tasks. Standard RAG chain is deterministic, following a hard-coded path. Embed, query, database, generate output. In contrast, an AI agent can evaluate the situation, select the right tools, and adapt its actions on the fly. For example, while a RAG chain might only fetch document text, an agent could check current stock prices, calculate balances, and send email alerts all in one workflow. RAACT Reason plus Act design pattern is central to agent orchestration. Here, the language model alternates between reasoning steps called thoughts and action steps. The model explains its strategy, emits an action specifying a tool call, waits for the result, and then repeats the loop. This structured approach ensures transparency and traceability in complex agent workflows. See RAACT in action. Suppose the agent needs to find the population of Paris in 2024. It first thinks, I need to use the Google search tool. Then it performs the search, receives the result, and decides how to format the final response. This loop of reasoning and acting continues until the task is fully resolved, making the agent's process both logical and auditable. Microsoft's Semantic kernel is an open-source SDK focused on integrating language models into enterprise software. Unlike LangChain, which is popular for rapid Python prototyping, Semantic kernel is built for large-scale production supporting C, Python, and Java. It offers features like native dependency injection, strict type systems, and modular plugins, making it ideal for enterprise environments. Imagine a large company with a net codebase. With Semantic Kernel, they can inject AI agents directly into their secure Azure C# microservices without needing separate Python environments. This seamless integration streamlines development and ensures enterprise-grade reliability and security. Planners are algorithmic components in Semantic Kernel that analyze a user's goal and generate a structured execution plan. They scan available plugins, use the language model to create a sequence of native code and semantic steps, and orchestrate the workflow to complete the task. This automation boosts productivity and reduces manual coding. Suppose a user asks to archive a text file and email a summary to accounting. The planner identifies the right plugins like file compression and send email, then generates a programmatic pipeline to pass data between them. This hands-off approach lets users automate complex workflows with simple instructions. LangGraph is an extension of LangChain that enables stateful multi-actor agent networks using graph structures. Unlike standard sequential chains, which are linear and rigid, LangGraph allows for loops, cyclic execution states, and human-in-the-loop validation. This flexibility is essential for building robust, real-world AI systems. Consider an agent graph with a code writing node and a code testing node. If the tester finds a bug, the data is routed back to the writing node for fixes. This cycle repeats until all tests pass. LangGraph's architecture supports these feedback loops, making it ideal for iterative, collaborative agent workflows. Modern frameworks export structured JSON schemas for tool functions, detailing their names, parameters, and constraints. The language model receives this schema and, instead of generating plain text, outputs a structured JSON object matching the function's requirements. The framework then parses this JSON, runs the code, and returns the result to the model. Frontier models like GPT-4o and Claude 3.5 Sonnet are fine-tuned to detect when to call external helper functions. Instead of continuing a conversation, the model outputs structured JSON arguments that match the required format. This reduces parsing errors and ensures reliable integration with external tools, making applications more robust. State management is the backbone of multi-agent collaboration. It tracks shared variables, chat histories, execution flags, and outputs as tasks move across agents. This centralized persistence ensures all agents remain aligned, preventing miscommunication and data loss during complex workflows. Imagine an AI travel agency system. The hotel booking agent writes the selected hotel into the shared state object. The flight booking agent then reads this state to coordinate an arrival airport near the hotel. This shared state ensures smooth handoffs and coordinated actions across specialized agents. CrewAI and Microsoft AutoGen are two approaches to multi-agent orchestration. CrewAI lets developers define agents as structured workers with roles, goals, and tools, orchestrating them in workplace-like workflows. AutoGen, on the other hand, configures agents as chat loops that collaborate by passing messages to solve tasks. Each has its strengths depending on the use case. A marketing team might use CrewAI to define a content writer agent and an editor agent, working in sequence to produce blog posts. Meanwhile, a research team could use AutoGen to let coding bots chat and collaborate, discovering and fixing bugs together. These frameworks make multi-agent collaboration practical and scalable. To prevent agents from trapping themselves in infinite execution loops, developers set explicit halting boundaries. This includes configuring a maximum number of iterations, enforcing runtime duration timeouts, and tracking history to detect repeated actions. These safeguards ensure agents exit cleanly when tasks can't be completed. Suppose an agent keeps trying to scrape a broken website. After 5 failed attempts, the runtime engine intercepts the loop, alerts the user, and exits. This prevents wasted resources and ensures the system remains responsive, even when faced with unexpected errors. Human-in-the-loop (HITL) orchestration allows agents to pause and await human review before proceeding. In graph architectures like LangGraph, this is done by setting a breakpoint on a sensitive node. The system saves the state, waits for human approval, and resumes execution once feedback is received. This ensures safety and accountability in critical workflows. Imagine an automated financial agent that creates a wire transfer. The system triggers a breakpoint, displays an approval button for an administrator, and only processes the transfer after approval. This pattern integrates human oversight into automated agent workflows, balancing efficiency with control. Tool convergence occurs when an agent is overloaded with too many tool options. This can flood the model's context window, causing confusion, parameter hallucinations, and poor tool selection. Limiting the number of tools per agent improves accuracy and reduces errors. Instead of giving one agent 100 tools, split them across 5 specialized subagents with 20 tools each. This division reduces confusion and helps each agent make better decisions, leading to more reliable and efficient workflows. LangSmith is a DevOps platform for monitoring, testing, and evaluating LLM applications. It tracks detailed telemetry including prompt trace trees, token counts, API latencies, pricing per step, and success or error rates. This visibility helps teams optimize performance and troubleshoot issues in production. For example, an engineering manager might use LangSmith to discover that a chatbot agent took 12 seconds to respond because a subchain ran redundant searches. With this insight, they can optimize the workflow, reducing latency and improving user satisfaction. A semantic memory plugin lets agents persist long-term context and episodic history across sessions. It saves important facts as vector embeddings in a database and retrieves them when relevant in future interactions. This enables personalized, context-aware AI experiences. Suppose a user tells their assistant, "I'm allergic to peanuts." The semantic memory plugin saves this fact. Months later, when the user asks for restaurant recommendations, the agent recalls this memory and filters out options that use peanut oil, delivering a safer, more personalized experience. To ensure agents output data matching complex JSON schemas, developers use pedantic data models with structured constraints. By binding these models to the agent's function calling architecture, you guarantee that outputs adhere to the required format, making integration with databases and APIs seamless. An automated invoice processor might use a pedantic schema with fields for invoice number and total tax. When the agent processes an invoice, it returns a structured JSON object that can be loaded directly into an accounting database, ensuring data integrity and reducing manual errors. Token streaming sends generated text tokens to the user interface in real time as the model outputs them. Using standards like server-sent events, users see results instantly, reducing perceived latency and assuring them that the application is actively processing their request. In a code generation app, instead of waiting for a long script to compile, streaming prints out lines of code as they're generated. This allows developers to audit and understand the logic in real time, improving transparency and user satisfaction. The agent executor is the runtime controller for agents. It manages the execution loop, sends data to the language model, parses tool calls, executes tools, handles errors, updates memory, and terminates the loop when the task is complete. This orchestration ensures agents run smoothly and reliably. If an agent outputs a malformed tool call, the agent executor catches the error, formats a corrective message, and passes it back to the model for automatic correction. This self-healing loop minimizes downtime and ensures robust, error-tolerant workflows. Simple string formatting just inserts variables into text. Formal framework prompt templates, however, support conditional formatting, manage roles across chat protocols, provide serialization for version control, and integrate few-shot example selectors. This makes prompts more powerful and adaptable. Prompt template can take an array of chat logs and automatically format them for different model providers, such as OpenAI's roles format or Anthropic's XML blocks. This flexibility allows developers to support multiple providers without changing core application logic. We've covered the essential frameworks, patterns, and tools that power modern AI agents. From LangChain and LCEL to Semantic Kernel, LangGraph, and advanced orchestration strategies, you now have a solid understanding of how these components fit together. Whether you're building chatbots, automating workflows, or deploying enterprise AI, these concepts will help you design robust, flexible, and scalable solutions. Thanks for watching.